Hello guys, how are you doing? I'm Rahul and you are watching the Concept Builder. And today guys, we are covering a new topic of the distillation, and which is the flash distillation. So if you are a student of the college, or if you are preparing for the GATE exam, or if you are preparing for the interview, watch the video till the end, because we're gonna use the Aspen plus simulations and animations to clear these concepts of the flash distillation. Okay, so let's get started. Okay, so the first question come to your mind is, what is flash distillation? So let's see its definition. So what does it say? If a sufficiently hot liquid mixture is throttled, and here the throttling means pressure is reduced, then a part of it will vaporize. The vapor will be rich in more volatile component, and this is the thing we actually saw in our first video, that I told you that when the liquid and vapor are in equilibrium, the vapor will be rich in more volatile component over here, and that's what happening over here, that using the throttling, we are doing that we are trying to establish the equilibrium between the liquid and vapor. Okay, we're gonna reduce the pressure such that a part of it will vaporize. That means there will be some liquid, there will be a part of liquid which is now vapor, and there will be equilibrium between them. Okay, so this is the basic idea how we are doing using the pressure reduction technique. So let's see what we're gonna do. So we're gonna take our feed. Okay, so this is our feed liquid mixture. Then we can use a heat exchanger if required. So here says that a sufficiently hot liquid. So if temperature is not what we want, then we can use the heat exchanger. Then what does it say? That pressure is reduced, so we have to reduce this pressure so that the vapor will vaporize, the liquid will vaporize, a part of liquid will vaporize. So here we have the wall, okay, which will reduce this pressure, and here we have a flash drum. So when the pressure will be reduced, what will happen, that there will be some liquid and vapor. So out of the feed, some part will vaporize into the vapor and the liquid. So we will have a vapor and a liquid, and both will be in equilibrium. So, and if you want the top product, the vapor as a liquid also, then you can apply a total condenser which will condense all the vapor, and you will get your product. And the important thing over here is the equilibrium. So you have to remember this, that in ideal flash distillation there should be equilibrium between the vapor and the liquid, so both are in equilibrium. That's easy guys. But here some questions that may come into your mind, that how much pressure to be reduced, what will happen if all liquid vaporize, and how to decide the final pressure. So I told you that we have to reduce the pressure for the liquid to vaporize, but how much pressure to be reduced, is there any range of pressure like that? So to answer all the questions, now we're gonna move to our Aspen plus simulation. So we are at our Aspen plus simulation window, and we have our flash separator. So okay, so let's define the feed. So this is our feed, and this is our vapor product gonna be here, and this is our liquid product. Okay, let us rename this. So I'm gonna rename as feed distillate, and the bottom product. Okay, so here I'm defining our feed as a mixture of ethanol and water, and our feed is at 100 degrees Celsius, and the feed pressure is 2 bar. Okay, so this is important thing, you have to remember that feed pressure is 2 bar, and I'm assuming ideal behavior, so our mixture is ideal. And let me define our ethanol as 0.4 mole fraction, so it's only 40% ethanol we have. Okay, now let's see, let's go to our block. So let's go to our flash drum. Okay, so this is window for our flash drum, and here I'm going to assume that there is no change in the temperature, and the pressure is now reduced to 1.5 bar. So initially we had 2 bar, and now it's 1.5 bar. Now let's see what we get. So I have started the simulation, and let's see the results. Okay, so here are our results, and you see that the mole fraction of our feed was 0.4, and in the distillate we have 0.59 mole fraction. That means that our vapor is rich in MVC, but you can see the amount is very low, only 2.2 moles out of 100. So we see that the amount is very low. Now I'm gonna reduce its pressure to, let's say, 1.3. okay, so we are doing more pressure drop, and let's see what happens. So I'm gonna just run the simulation. I have zoomed in on the screen so you can see easily. So let's go to stream and now see the results. Okay, so here we see that the most of the liquid has been vaporized. You can see the flow rate of our D stream of our D is very high. Okay, so you can see that there is no such a mole fraction change, and the most of our liquid has been vaporized. So we see that okay, so now let's see what happens if we reduce pressure to 1 bar. Okay, so for now it was 1.3, and now we're gonna reduce to 1 bar. Okay, so when we're gonna do it, let's see what happens. Okay, so now our pressure is 1 bar from the 2 bar. So feed was at 2 bar and our flash drum was at 1 bar, so that's why we reduce the pressure. Okay, so I'm gonna go and see the reports. Okay, streams, and here you can see that there is no liquid fraction, only D is here, there is no bottom product, and you can see that all our liquid has been vaporized. So it tells us that there should be a range of the pressure. If you reduce beyond it, there will be range. Then we have to ask ourselves that how to find this range. So in Aspen Plus also we can draw the PXY data. So in the previous video we talked about TXY diagram, and with the help of experiment data we can also draw the PXY diagram, where P is the pressure. So we can find out the range in which we should do the pressure drop, such that we get liquid and vapor. Otherwise we will vaporize all the liquid, and the flash operation will not happen. Okay, so we are here at this screen where we can draw the PXY diagram, and I'm gonna draw it at 100 degrees Celsius, and here are several options. You can choose other temperature as well. So this is our PXY diagram, as you can see, and this is very important. So here you can see that the region or the top is the liquid region. Okay, and in the bottom there is a vapor, because at high pressure there is a liquid phase. So we have to see. Okay, so we have to see where is our feed. So you can see that it was at 0.4 mole fraction and 2 bar. So if you can locate this, you can see over here, and you can see that the region between the blue and green line, this is where our phase separation will occur. So you have to pressure drop such that the final pressure should be in this range. Okay, so from here we can see the range. So it was a good concept. You should remember that there is always a range in which you should do the drop. Otherwise, if you go beyond that pressure, you will get only vapor and there will be no separation. So it was important concept for the interviews, so they may ask in your interview. Now we're gonna move next to our thing where we're gonna do some kind of material balance and all that to find a formula, because in exam we need a formula to solve the thing. So okay, sir. Okay guys, so we have seen the Aspen Plus simulation, and now what we're gonna do is we're gonna apply the material balance, and we're gonna trying to find out some relation between these terms. So we have feed over here, and we have this flash drum, the flash column, and we have our vapor product and our liquid product. Okay, so here are some terms you should recognize. That F is the mole per second, the flow rate of the feed, D is the flow rate of the vapor, and the W is the flow rate of the liquid. Y and X are its mole fraction, the composition. Okay, is it clear? And the mole fraction of the feed is ZF. Okay. So this is these terms we're gonna use, and now what we're gonna do is we're gonna do the material balance. So first material balance we're gonna do is overall balance. So we take that whatever come in should go out. To do like feed came in, so feed equal to D plus W. So this is our overall material balance. Okay, and now we're gonna do the component balance. So in the material balance, if you have learned this subject before, then you know that first we do the overall balance, then we do the component balance. And here the component balance we're gonna do on the more volatile component, because here every information we have given. So let's do it. The F into ZF, this is mole fraction of the feed, equal to dy plus Wx. So it's very easy, you know, it's a simple component balance, right? If you solve this, so if you put the value of F from here, from the overall balance, you will get this equation, and after just solving it after just simple rearrangements, you will get this equation, and this equation is the important formula of the flash distillation. So what one thing I would say to remember about the flash distillation is this thing, this formula, that minus times, this is the negative times W by D. So W is the liquid flow rate and D is the vapor, okay, equal to Y minus ZF divided by X minus ZF, Y minus ZF divided by X minus ZF. So you have to remember it somehow. So if you know the mixture rule, then you can get this formula from the mixture rule also, and also from this simple component and material balance. So these two equations are very important, and from this the equation we get over here, this W by D negative times equal to this thing, and this you have to remember because you will need this. Okay, so there is one more equation. If we define the fraction of feed vaporized, which is D by F, because the D is the vapor formed and F is the feed we initially had. So D by F is the fraction of feed vaporized, and we define it by the small f. So if you define this thing, the small f over here, then we can get this equation. And how we got this equation? We got this from our this material balance. So in this material balance, if you divide the first equation by f, then you will get one equation, one formula, and also if you divide this equation with the f, then and using both the equation you can get our final equation, and this is your homework. You have to try it yourself. Okay, so this was your homework. As a homework you have to do this, and finally you will get this equation. This z over here is the zf. Okay, I'm just writing over here is a z, and so what is this equation? Y, the small y is the mole fraction of the vapor, equal to f minus 1 by f. F is the fraction, and x is this x, plus z is this, and it is divided by the f, the small f. Okay, so this formula you should write down in your notebook and remember it. You may need this because in the question, if they said that you gave a particular amount of feed and let's say 50% of this vaporized, or they can say that 80% vaporized, then what will be the mole fraction of the vapor or the mole fraction of the liquid, whatever they can say. Okay, so this thing is important. Now let's move next to the more important part and the last most important thing. Okay, so let's see what we have now. Okay, so far what we have, this equation, this thing over here, which is important. Okay, so now we have this y-x curve. So in the first video when we studied the txy diagram, and also we talked about the y-x diagram or the xy diagram. So this y and x diagram, this is y-axis, this is x-axis, and y-x are the mole fractions of the vapor and liquid products, and this line is the equilibrium line, you already know. So let me show you just like this. Okay, so this line over here you see is the equilibrium line, and this is y equal to x line. Okay, and the main thing about this y equal to x line is that we represent our feed on this line. So we have our feed which has mole fraction this one. so we represent our feed over this line. So this is our initial point. Okay, here you can see this is our initial point, and this is our y comma x. So this is y, this is x, and this point is y comma x. So what we did that we started from here and we move over here. Okay, so this is what happened over here. Is it clear? Okay, so is it clear? So this line is also called as tie line. So this line is important, and here you can see the important thing I'm gonna show you over here, that can you determine the slope of this line? This is straight line, and what is the slope of straight line? Y2 minus y1 divided by x2 minus x1. So what is y2? It is y minus y1 divided by x2 minus x1. And if you see over here, this is nothing but the slope. So what we got from this, our main formula, our main equation is nothing but the slope of this operating line. Our equation, our main formula was nothing but the slope of this line. So guys, this is the last and the most important part of our video. So we're gonna take a leave. So guys, thank you so much for watching, and if you're new to this channel, subscribe and press the bell icon so that you can receive notification when we upload the video. And also in the description you will find some questions related to flash distillation, because after learning a concept it is very important for us to practice it. Okay, so what you have to do, open the description below and there will be some questions, so you have to solve the question and comment your answer in the comment box. And if you like the video, you can share it to your friends who are also preparing for the GATE exam or in college exam or whatever they are doing. Okay, so you have to share to your friends, and that's all. So we'll see you in our next video.